Yeah, good morning, all of you. Thanks to Sydney. As he said, we couldn't work out last 2 years. There were all kinds of issues, so this is the third time it worked. So I'm very pleased to come here to Perth and trying to share some of the things what we have been doing in our group for the last several years. So I'll be giving 2 talks. So today's focus is more on the scalable DNN training, and tomorrow I'll be going into more details on convergence of HPC, AI, and big data kind of things. So as many of you know, I mean, Rob gave a very high-level overview in the morning. We are in a very exciting phase in the community called deep learning. So this you can see like a typical thing. The deep learning is a subset of a representation learning, subset of machine learning, and also the subset of AI. So a lot of actions are happening along this line. I just want to indicate that, of course, a lot of these things were available, as Rob indicated in the history. A lot of things were available concept-wise, but people were not able to really compute all the theory, and that's what we are seeing being changed over the last several years. So that's why there is a lot of new interest, but I also want to emphasize that these days there is also a lot of hypes. To be realistic, I give this example, those of you who are professors or even writing papers or even in the companies, you might be doing exactly the same work. Just change it, just add 2 more words, deep learning or AI, then you will see your paper gets accepted, your proposal gets accepted, okay? So that's what I call it, like a hype, because everybody is in the same boat, and there's nothing wrong here. I mean, many times newer technologies come or newer areas come and everybody jumps into that, and it takes some years to break even and to find out what works and what doesn't work. But anyway, we'll keep that in mind, and these are some of the the data what people have been talking about, like deep learning. On the left hand side is trying to show the market prediction, a 2025 it will be coming more than a $35+ billion market. But more importantly here, almost every discipline, people are trying to explore how they can use AI or deep learning, machine learning to improve the performance, scalability, and also newer kinds of capabilities. So the broad challenge, what I try to focus here is that how we can use this kind of a convergence in terms of HPC, big data, as well as deep learning. And we are in a very positive cycles here. I mean, we have HPC hardware, then also the big data frameworks are coming, and people are trying to exploit both HPC and big data into the deep learning. So as long as we are in a positive cycle, this is like economy, we are in a positive cycle, everything looks good, and everybody gets benefited, kind of thing. And not only people are trying to explore these things on dedicated machines, also there is a lot of focus these days on to run these also on the cloud. So we'll take that as a much more bigger picture. And before going into more details, just trying to show how the big data and deep learning things are coming together. So this is a kind of newer directions coming, deep learning over big data. So for example, here if you see a Flickr pipeline, so you can think of you have some huge data sets, you want to prepare the data set at scale, might be then trying to do some deep learning. You may also try to run some non-deep learning, and also finally trying to apply some ML model. So if we can have a convergent software stack, it allows people to explore all these different kinds of workflows. And these workflows were not feasible earlier unless you have a convergent software stack. And if you can build some hardware and software to enable these, it opens up a lot of new opportunities. So with that kind of a background, so let's take a look at what is happening in the modern HPC systems. As many of you know, there is a lot of focus these days on multi-core, high-performance interconnects like InfiniBand, accelerators, FPGAs are coming, and also from the I/O side, there is a lot of actions taking place in terms of the NVMe SSDs, which is more trying to combine RDMA with SSD, just like what has happened in the last several years with RDMA with networking, RDMA being combined with accelerators. Now the next phase is going to the RDMA with SSDs. And with respect to deep learning, as we have been hearing like the last two talks, many of you know there are two phases. One is the training phase and then the inference phase. And the training phase is the mostly time consuming one. So this is where a lot of actions are taking place. How do you take the capabilities of the HPC machines to make it faster? And this is where the parallel and distributed training comes into picture. So I want to explain the challenges in this diagram where people have been exploring both the directions. Like we want to have good scale up and also we want to get good scale out. The scale up in terms of like within a single node or a single server, if I put on adding more number of GPUs or keep on adding more number of CPUs, can I scale my job? So that is within one server. Of course, there is some limit to what you can achieve within the node. So then we need to scale out to have more number of nodes. So in this context, there is a lot of different software components are being worked out. So here from NVIDIA, we have CUDNN. From Intel, we have MKL DNN. From NVIDIA, also this Nickel 2 library. We are trying to focus a lot on the MPI-driven solutions. That's what I'll be talking a little bit later. And of course, there are also some solutions people are working on big data with the Hadoop or even like a TensorFlow or gRPC. But the broad goal, irrespective of what kind of software stacks you want to use, you want to reach this corner so that we can have the both scale up and also scale out. So that is the kind of the goal. So then the question is like a lot of times you see a lot of these numbers. In fact, many times when people try to show some numbers, how do you know that those numbers are correct? Okay. So in fact, from our group, we did a study and published this paper 2 years back at the MLHPC 17 workshop in conjunction with the supercomputing conference. So what we indicated that anytime you try to present some numbers in the deep learning area, there is a holistic evaluation is important. So what do we mean by holistic? So the idea here is that if you take the stacks, so of course we have all the hardware here, and this is your actual DL applications, like think of like image recognition, speech processing kind of things. So then below that, these are the frameworks. People talk about Caffe, TensorFlow, PyTorch, or whatever is your favorite deep learning frameworks. But then below, this is the thing which plays a very important role for the performance. Okay, so these are you can think of like because all these DL frameworks inside, you have some convolution layer or MKL optimized convolution layer or the NVIDIA convolution layer. Then you have all these BLAST libraries, Intel's MKL DNN, the CUDNN. This is the most important part. Okay, of course, continuously newer and newer drivers are coming out from different organizations. So when you want to evaluate it, try to make sure that whatever is the latest hardware, all these components are optimized. If you don't do that, you will see very drastic differences in the results. Okay, so I want to give this like a 4-layered structure first in account. So in this context, what we want to achieve as a community and also from my group, this is like a research agenda we have been working for the last several years, how to efficiently scale out deep learning framework and take advantage of heterogeneous HPC resources. Okay, at this time heterogeneous again, primarily focus on like the CPU plus GPU. So I'd like to give 4 broad challenges, how people have been working here. So the first one is, if you just think of this like a hierarchy, we have all these different frameworks here, and then of course all these we have take an example like a CNTK, Caffe and all, and of course these have different kinds of computation and communication phases. So if you are an HPC person, you can think of these frameworks themselves are like an application. Okay, so just like in an HPC, you might be having a scientific application, like a molecular dynamics or computational fluid dynamics. So all those issues, whatever we do there, like trying to balance computation with communication, trying to have overlap between computation and communication, trying to reduce the communication overhead. So all those issues exist here. Okay, so that's the first set of challenges. So when you are trying to use some framework, you may need to see that those frameworks themselves are optimized properly. Okay, I'll show some examples later on. We have done some co-designing work. So when the frameworks are not good, then no matter what you do, you don't get the good performance. So you have to optimize those frameworks. The second one is the communication runtime, because now you have the communication frameworks and we are trying to run on a parallel system. So in this context, we have to make sure that your communication runtime actually supports that. So here in this context, we have to make sure like all the components like the CPU or network like InfiniBand, GPU have delivering the best performance there to support this parallel and distributed training. The third one is to go inside and trying to see what is the most critical in that communication runtime. And here I want to focus on two things, and I'll go into more details on later on. One is the first collective communication. Okay, and like operations like all reduce, operations like bcast. So these are the kind of operations which are very common in all these deep learning applications, and these are nothing new. If you would have written some MPI programs in the past, you will see that these kind of operations are also there. But there is a little bit of difference in the sense, like let's say you take a traditional MPI application, it might be using all reduce, but the all reduce was being used for only 8 bytes or 16 bytes. Whereas in the deep learning, it totally changes. You want to do all reduce over like 16 megabytes, 16 gigabytes. Okay? So that means from a runtime perspective, whatever the algorithms were designed for the traditional MPI stack may not hold good on the deep learning side. So you may need to rethink how these algorithms need to be redesigned so as to deliver better performance for the deep learning applications. And also I'll try to introduce some concepts of CUDA awareness because a lot of GPUs you are trying to use these operations. So when the kernels do the work, so data is ready. So how do you move this data out? Okay, so I'll introduce the concepts of CUDA aware MPI. Those kind of concepts help you to move the data very efficiently. And then finally, this is the kind of the co-design I was hinting at. So when you have all these components, now you have to do an integrated evaluation and then see whether all these components are matching together or not. Okay? And to deliver the best performance, you may need to totally look at the complete stack, and then where you see that if there are some inefficiencies, you try to improve and get the best performance. So we'll keep this kind of 4 major challenges in mind as we go through the next set of slides. So these are the different ways my group has been trying to address this community. As some of you know, I mean, we have been working in my group almost for last 30 years in trying to design all the different kinds of communication middleware, communication runtime. I'll go into some more details. So first I'll try to focus on MPI-driven deep learning. So that means how the MPI, the traditional middleware, which is being used for the HPC machines all over the world, can also help you in the deep learning. Okay? So I'll try to focus on CPU-based deep learning as well as GPU-based deep learning. I'll try to give an example of co-designing, and also I'll try to show some newer challenges, whatever is coming, called out-of-core DNN training. Okay? And then after that, I'll try to go into some other examples, like how do you accelerate TensorFlow, like a TensorFlow over GRPC. That is one of the common one people have been using. So how you can optimize that on InfiniBand kind of systems or networks like RDMA. And also how do you accelerate the traditional big data stacks like Hadoop and Spark, and also the associated deep learning framework. So I'll try to cover this in 2 phases. So now let's go into a little bit deeper, and I indicated all these collectives. So where these collectives are coming, okay? So if you take a look at like any kind of a deep learning, we know there are multiple phases, forward pass, backward pass. So this tries to show where those collectives come. In the very beginning, might be what do you need to happen, that you need to send the data to all the GPUs. So we have all these, let's say, image training you are trying to do. Depending on the batch sizes, we are getting the images from the IO subsystem and trying to push those into the GPUs. And this is where like all the different parallelism we talked about, like Rangan gave an overview, like data parallelism, model parallelism, hybrid parallelism, depending on the scenarios. So here you can see how to push those data. So this is where one such collective might be a bcast or a broadcast, MPI bcast might be more common. So then you go into all this training. So this is the forward and the backward pass, and then you try to get the results, SGD, and then you are trying to, again, bring all these things to the gradients. And so this is where you can think of like a reduce is being used. Okay? Or sometimes what you can do is, after this reduce, when you again go, this reduce and bcast, you can combine it as a all reduce. Okay? So these are the kind of the very 3 common collectives you see in all these kind of a deep learning frameworks when you go into the distributed training. So the overall performance will totally matter on how you optimize all these collectives. And that's what I'll try to show the results later on, depending on the different frameworks, different middleware, whichever stack can give you the best performance for these collectives, you will see the overall you get very, very good performance. So in this context, let me expose you to this MHAPITS project. So this is the project we have been carrying almost 18 years now. So we started this project almost the day one of InfiniBand. In fact, prior to that, in my group, we were working on the older kind of interconnects like Mirinet, Quadrix, and all. So when InfiniBand was introduced in October 2000, we were the very first ones in the world to jump in and then trying to say, okay, how you can have an MPI library which can actually try to exploit the native RDMA concept of InfiniBand. Okay? So we had, in fact, the first demonstration of our open source stack in the 2002 supercomputing, and many people cannot believe by that time, like 2002, running an MPI library over an InfiniBand system on 8 node was challenging. Okay? It was not even reliable on just running on 8 node. And now you see whatever has happened in the community. People are running over 6,000 nodes, 8,000 nodes, #1 Summit, all these systems. So that has happened over the last several years. So from my group, we have been an enabler of this community, trying to continue and trying to see how this technology can grow over the years. So we started that from very basic MPI 1. Of course, over the years, we have a lot of different versions. I'll be talking about that soon. So currently, this software stack is being used by more than 3,000 organizations in 89 countries. So these are based on voluntary registration. A lot of people download from our website. They don't register. That's perfectly fine with us. And last November, we actually crossed 500,000 downloads just from our website, this project site. Of course, MPI Stack is available in a lot of other vendor stacks, as well as like OpenHPC, SPAC, and a lot of package managers. We don't keep track of those, but these are just the pure downloads from our site. And not only is the number of downloads, but of course, it has been enabling a lot of these top 500 systems over the last decade, continuously trying to push the frontier. Currently, in fact, the earlier talk, Rangan indicated this track Frontera system, which is being deployed as the number 5 system in the world in Texas Advanced Computing Center. So I'm actually a co-PI of that grant. So that will be one of the top machines in the US academia to use this kind of systems. So the overall architecture of this, our MPI software stacks looks like this. And it tries to address, even though it is for MPI, we try to take care of this both HPC and DL. So that is the kind of the convergence I'll be talking later on. So we have support for pure MPI, even pure PGAS models like UPC, OpenSMEM, etc. And also we can combine, mix and match. In the same program, you can have some parts running with MPI, some parts running with OpenSMEM, and you can run that with our unified runtime. Okay. So then, of course, at below, we support all the different networking technologies. We started with InfiniBand, but we also support all the IWAR, Rocky, Omnipath. In fact, very recently, we provided a support for the Amazon AWS, the EFA adapter. We made a release just 3 weeks back. We support that. And we also support all the different kinds of the platforms, starting from the x86, OpenPower. We have been supporting Xeon that has gone down, ARM, NVIDIA GPU, so all the platforms we support. But the broad challenge is this layer, and this is where in my group, because we are from academia, we focus on the designs, like which designs, like all these networking technologies and platforms give us a lot of newer kinds of mechanisms and ways to design the runtime. So I call my group members saying this is our supply side and this is our demand side. So we take all the features and try to take it through the runtime and then try to deliver you the best MPI stack for HPC and DL. So always like, because in a research group, we always come up with the first publications. And then once the papers have been published, in 6 to 9 months, we actually take these designs and then push it into our public version of the software stack. So even though we are in an university, in my group, we have very close to 200 machines continuously doing QA testing, okay, of the code. So it is not just like a university code, somebody pushes it. We really push it with a very rigorous testing. And now we have capabilities like within 36 hours, we know whether a code is able to stabilize or deliver the performance or not. So we check for all the logical correctness. Then after that, we do a lot of regressions. So then in 6 to 9 months time frame, you will see the designs are out to the public, and then we post the public release, and then everybody can use that. That's how we are able to maintain this production quality software stack. So there are multiple versions here. I may not have time to go over all. In tomorrow's talk, I'll talk about some of these things. But today, I'll be talking first like a CPU-based deep learning, and then I'll go into the GPU-based deep learning. We also have some versions for cloud, energy awareness. There are a lot of tools, including some InfiniBand network analysis and monitoring combined with the MPI stack. I think one of my team members gave a presentation on this last year. So if any one of you are interested in to know more, I am here today and tomorrow. I'll be happy to talk with you. But let's try to focus on the CPU-based deep learning. So as many of you know, even though like the deep learning, whenever people talk about deep learning, always GPU comes into mind. That is perfectly good because GPUs deliver a lot of capabilities. But if you see at a overall, CPUs-based clusters are always available. Okay? And also, if you talk about like some cost performance, you will see that the GPUs are still very expensive. Okay? So there is an opportunity even for people like when trying to learn, let's say deep learning or try to experiment, you always don't need all the big GPU clusters. Okay? So we are trying to enable the community also like, yeah, you can use the existing CPU clusters. So in this context, what happens, just like the traditional MPI works for HPCs, so now if we want to optimize for deep learning, the challenge is how do we optimize the collectives? Okay, so if we can optimize the collectives for this large data, so then the same stack you can actually use for the deep learning. And that's what we have done. So here, what we have done is, so here we are trying to show there is a solution out there. Tomorrow I'll go into more details on this. It's called an XPMEM. How many of you heard of this XPMEM module? Not many of you. So this is a kernel module based design. So as you know, like a lot of cores these days are within the server. I mean, the latest ROM architecture, if you see 128 cores. Okay. So if there's some color operations are happening, point to point and collectives within the node, how do you optimize that? So there is a XPMEM, which is a kernel based module. So it allows actually my address space to be mapped to your address space, and your address space can be mapped to my address space. So instead of message passing, I can do load store operations between those, and those are becoming much more faster. Okay? And that's what we have enabled in our MPI stack, the very latest several releases, we support XPMEM. And with that, if you see, then we optimize all the collectives. So here we are trying to show like a CNTK using all reduced collectives. This was presented in IPDPS 2018. So even at a 56 process, 224 processes, you see 10 to 20% benefit you see. The only difference is collectives. The entire stack, there is nothing else we are doing. Okay? You optimize the collectives, you see the benefits at the deep learning layer. Same thing here, there is another newer design we have done. So this got a best paper in the cluster 2018 last year. So we are trying to actually integrate it. It's not available publicly yet. So now you can see for a 896 process, if we want to run like a TensorFlow, you can get a boost in 35% performance. Okay? Because the way you are optimizing all the collectives, not just within the node, also across the node. So we take care of both of these, and then you can actually get a scale out for CPU-based learning. So then let me go into GPU-based learning. That is a kind of a lot of people have been using. So in this context, we have a very highly optimized stack. We call it MAP to GDR. GDR stands for GPU Direct RDMA. Okay? So let me, before going to that, I'll try to introduce this concept of CUDA aware MPI. How many of you heard of this term? Several people. So let's see what is that concept. So if you take a look at a cluster here, like I have GPUs here, there is a CPU, let's say there is an InfiniBand or any RDMA kind of networks. Traditionally, when you do GPU-based programming, always the idea is that if I have the data there, like you have launched a kernel, there is some data, and when I want to send the data, you do a CUDA mem copy to the host, and then you do an MPI send, and then the other end you do an MPI receive, and then you do CUDA mem copy. Okay? So this is very good. It delivers high productivity, but performance is very low because you are going through so many steps, you may not be getting the best performance. Of course, the productivity wise, it is much more easier to write, but at the same time, you'll see that the end users may need to learn all the CUDA stuff. Okay? And then there are, of course, some advanced users. What they try to do is, instead of, let's say, the same data, instead, let's say you have 16 gigabytes of data, instead of sending it as a chunk, you try to do some pipelining. So I can do a lot of CUDA mem copy async, and then move into the over the network. You do MPI isend, and then finally you get the data, do the operation. So in this one, we try to characterize that, yes, you can get some good performance, but productivity is very low. So forget about the DL. Even for MPI or in HPC applications, if you are a application scientist or a computational scientist, instead of them focusing on the actual science, they are trying to focus on CUDA programming. All right? So you spend a lot of time trying to understand CUDA, how much I should pipeline, try to take some measurements. So they are trying to become computer scientists instead of trying to remain on the computational scientist front. So then we ask the questions that can we come up with some way so that it will be high productivity and also high performance. So that's what we try to propose. So this was a paper in ISC 11 we proposed almost 8 years back. You can go and take a look at it. And so the idea is that if somebody knows how to write an MPI program from host memory, you just change, instead of like MPI send host buffer, you change to device buffer, and at the receiver, instead of a receiver host buffer, you say receiver device buffer. That's all you need to do. Everything else the MPI library will do for you. It will understand like where to send the data, how the topology, a lot of intelligence is there within the MPI library. And in this context also, GPU direct RDMA came at that time. How many of you know GPU direct RDMA? Okay, quite a few. So the idea is that if my InfiniBand adapter and GPU adapter are sitting next to each other, I can actually send the data over the network. Okay, so we took all these concepts together and introduced this library. So you can see that within the MPI library, it takes care of everything. Okay, so as an end user, you just have to change your program instead of like trying to take care of all this movement as I showed in the earlier one. Launch the kernel. After that, you just say, okay, send, where to get received. That's all. So this actually delivers high performance and high productivity. So we worked this in the 2011 and a subsequent set of papers, and then NVIDIA folks approached me saying, why don't we take this design and then push it into the MPI stack. So that's how this MPI GDR package came in. So over the last 8 years, we have been working very closely with all the newer features of NVIDIA and trying to continuously optimize our stack. And not only like we have done, a lot of other MPI stacks have also moved into this concept. Okay. So now if you try to do that, so this is like the latest, very latest release we have done. I'll show some of the numbers. We have done a lot of highly optimization here, not only for like a DGX2. In fact, we have scaled it on the summit, like this all reduce, which is very important, to 24,000 GPUs. So that is the entire system. We have scaled our all reduce within the library so that you get the best performance on the #1 system in the world. So now let's see what kind of performance you will get. So this is where like this CUDA where MPI shows the benefit. So look at this number, 1.85 microsecond. I can send data from a GPU of one node to a GPU of another node, not on the same node. GPU of another node over InfiniBand, small messages in 1.85 microsecond. If you look at the regular like a host-to-host communication, most of the MPI stacks deliver around 1 microsecond. In another 850 nanoseconds, we are able to move the data from GPU to the other GPU. That is for small messages. Medium messages, we get very good benefits in terms of bandwidth, unidirectional and bidirectional. So I'm very proud of my team who did all these designs, and gradually these designs are being replicated in other MPI stacks, and you will see very similar kind of performance there. So that is the kind of the beauty. If you make some fundamental changes internally, then you see like you will be able to boost the performance quite a lot. So today I'll be focusing more on the DL side. Tomorrow I'll focus on performance on the HPC side. In fact, for the last several years, if you have visited Switzerland, we are actually trying to work with Switzerland government to have real-time weather prediction using this stack. So if you open up your iPhone in Switzerland and try to look at the weather, we are trying to drive that. So I'll talk more about that tomorrow. But let me focus more on the distributed training. So in the distributed training, so there are a lot of solutions out there. Okay, so we did a very exhaustive search. So this is like the TensorFlow. Let's say take one of the framework which is very common. There are a lot of options. So there are broadly 3 different options. The initial design was through GRPC. So I'll try to show how to accelerate that later on. So then there is a solution, no GRPC. You either go through a specialized MPI like a Baidu MPI, or you go through Horobot. And then within Horobot, again, there are solutions whether you can link it with any of the MPI stack or go through the NVIDIA's Nickel library. So as of now, like this is the path which is getting a lot of momentum. Okay? But of course, there are some in-between solutions there also, GRPC plus X. So where to move the data, where to move the control. There are all these kind of solutions. So we did this study presented in the CC Grid 19. It is also available publicly. Please feel to take a look. So what we tried to say that in this paper, then we tried to see if you take this path, how we can provide the best distributed training. Okay, so I'll try to show some numbers here. So here we try to compare, like on a 16 GPU kind of thing on the ResNet 50. If you try to do so, here we compare like the traditional Horobot MPI, the default MPI, use the Nickel 2. So this is our optimized MPI stack, and then this is the ideal. So if you see this yellow bar, that is the ideal, what you can get. And if we can have our MPI stack with optimized collectives, we are able to get almost 90% scaling efficiency. Okay? So just like the traditional MPI stack, whatever is available on all the machines, including GPU clusters, now can be utilized for all the DL applications. You don't need any separate stack. Okay. So then we continue to optimize a lot of other MPI, collectives. And then here I'm trying to show again on a 16 GPU. This was a comparison with the Baidu already used and OpenMPI already used. And what we are trying to do here also, even though I indicated earlier, a lot of deep learning models are trying to use very large messages, there is still a lot of debates going on, saying is every deep learning will use the large messages, or some can still also use short messages. In fact, even the Horobot, if some of you would have looked inside, now they have trying to add a feature called fusion. So depending on where the data comes, you can send it or wait. So in that case, from a demand perspective, we are trying to optimize all message sizes, all reduce, and that's what any MPI stack can deliver. So here you can see, like compared to other MPI stacks for small, medium, large messages, we are able to deliver significant performance gain here. This is comparison with Nickel 2. NVIDIA, as many of you know, they have the specialized library just for deep learning. This is not a regular library for your HPC. So they have been like advocating, that is fine. But still there is a limit. So if you go through the MPI designs, so here you will see like on a 16 GPU, we can deliver you at an all reduced level almost like a factor of 3 and a factor of 1.2x performance benefit compared to the Nickel library. This is on a DGX2. As many of you know, the DGX2, NVIDIA is saying this is an AI machine. This is just a hardware. I mean, you can run any software stacks on that. You don't have to stick with any particular library there. If you take our MPI GDR library and then put it onto your DGX, so you see we can deliver you at the all reduced level, the small to medium messages almost 5.8x better, here up to 2.5x better. Okay. And then this is the latest study we have done on #1 system on the summit, up to 1,500 GPUs. Okay. So see the performance. So here we are trying to show like this is the latency, this is the bandwidth. So the red is our design, the green is the Nickel, the latest version 2.4. So here you can see like we can deliver you 1.6x better in latency. Bandwidth, you see that we are able to scale as the number of GPUs are scaling. We are able to go into 1.7x better performance. And then for a kind of a 128 megabyte message, which is very common, we compared even with other MPI stack, like the Spectrum MPI, which is the vendor provider MPI library for the Summit, and also the Nickel 2.4. And you can see that we are able to deliver purely MPI-based solutions. We are able to deliver very well. In fact, some of the other MPI stacks didn't run properly at this scale. So then similarly, it is not just the basic performance. This is the ResNet 50 training using the TensorFlow on the DGX2. So here again, you can see that we are able to deliver like images per second. That is kind of the metric. Not only we are able to deliver higher performance, but the scaling efficiency we are able to maintain. So that means as you go into larger and larger number of GPUs, we are able to sustain the performance for more number of nodes. And then this is the very latest results, just a few weeks back, many of people have not seen. So we took actually, this is on Summit, we took ImageNet 1K. It has 1.2 million images. Okay? And we ran it on, again, the Summit, 1536 Volta GPU, 1500 GPUs. And here, actually, the nickel didn't even run. It broke after 96 GPUs. But whereas we were able to scale to 1500 GPUs, and we were able to get like a 0.35 million images per second on this Summit system. And if you do some math, here you will see that we are able to now train this ImageNet 1K with 1.2 million images just in 5.5 minutes, kind of things. So the solution, what I'm trying to provide you is like, hey, you should be able to run it even on your small x86 cluster to DGX2 to the #1 Summit. So all these platforms, you should be able to run our stack and then get the far better performance compared to the other middlewares. And to download this, anybody can download and install this. If you go to our MapIS2 webpage, you have the very detailed instructions, and you don't have to be even a root user. Many times people say, oh, I can't use your stack because I don't have root access. So we have actually provided non-root access. So as long as you have an account, you should be able to download, follow these steps, and run your libraries, okay? And to get the best performance. So then let me move ahead. So that is kind of the basic performance. And then the next step, I talked about this co-designing part. So this is the work we did like 2 years back. So the idea just I want to give, like a lot of these frameworks, they are coming from the AI side. Like people who have done the Caffe or TensorFlow, Caffe2, PyTorch, these ideas are coming from the AI world, that is good. But then those people don't have a lot of HPC background. Okay? So when they write these applications, or rather the frameworks, a lot of steps are not optimized. You open up some of these frameworks, you will see, for example, when we started this work on Caffe 2 years back, look at the broadcast phase I indicated. So they just do the broadcast for I is equal to 0 to n-1 MPI send. I mean, many of you will be laughing, saying, okay, what is this framework is trying to do? Because that phase, if you do like this sequential one, you will totally get limited by the performance. I mean, HPC people for 30 years know how to do a very efficient broadcast. Okay? So like this, if you go through a lot of these steps in the framework, you will see the frameworks themselves are not optimized. Okay? So we did this co-designing. So this paper was presented in PPOP 2017. And that time, with this co-designing, we were able to demonstrate like it can scale to 128 GPUs, where the community was struggling to scale with 816 GPUs. Okay? So we are taking similar ideas to the recent frameworks. I don't have all the results here yet, like the TensorFlow, the PyTorch. We are looking at all these latest frameworks. But if anybody wants to experiment with these, this is available from our website. We have a project called High Performance DL. We call it HIDL. We are trying to bring HPC plus DL together. Please feel free to take a look. So then we are working on this issue I indicated, like which is out of core DNN training. So what does that mean? So these days, as you know, these models the sizes of the models are exploding. Okay? People have been adding more and more number of layers, more kind of nodes, edges. So then the question is, if I want to run it on a GPU, can I even fit my model there? So you take like a latest Volta GPU, let's say it is at 16 gigabytes. If your model size is bigger than 16 gigabytes, so how do you run even a DL application? Okay? So that is the challenge we are trying to solve here. But if some of the old timer HPC people are here, this is not a big concept from the HPC or a big challenge. From the HPC side, even 20 years back, people were trying to see, okay, how do I do out of core sorting? All right? If your memory cannot hold all the data, how do you do out of core sorting? So we took a lot of those ideas back and trying to apply it into out of core DNN training. So this paper was presented in HPC conference 2018. So the broad idea is that even though like you have all these layers, when you try to take a look, it is not that the actual training is happening in all the layers at the same time, exact same time. So that is the key thing. So I don't have to fit all the layers within the GPU at a given time. Okay? So that is the clue. And if we know that, then we have a lot of solutions. And of course, NVIDIA has this managed memory concept, where you can move data between host memory and GPU memory using the managed primitives, and we try to take advantage of that. So in the background, it is a user transparent operation. The user doesn't have to worry about it. So first few layers, we push it into the GPU. While the things are taking place, the other layers are being staged to go to the GPUs, and the older layers come back to the host. Okay? So if you use that, so then there is no limit. Any large kind of a DNN model, we should be able to run it on a GPU. So this we have done again like a prototype design on the OC, we call it like out of core cafe, but ideas can be applied to any of the other frameworks to be done. So then let me move into the next kind of a topic. So those are like purely MPI driven solutions. Okay, as I said earlier, I mean MPI libraries are available on all different platforms, CPU, GPU, and if you want to do, and these have been optimized for all the platforms for last 20, 30 years. So now with the deep learning, exactly the same thing you can use. You don't need any other different kind of a middleware. Okay? But still people are trying to use other stacks. So here I'll focus on, one is the TensorFlow over gRPC. This is where it started, the Google's TensorFlow. The gRPC stands for Google RPC. So this is the architecture of the Google RPC. We have the server, we have the client. So what we have done, just like our MPI stack, when we started like 20 years back, all the MPI stacks were running over TCP/IP over sockets. And we're the very first ones to take it to the InfiniBand native bursts. Okay? And over the years, we have been doing that for all other stack. I'll also try to show the big data stack. So here what we did is, we applied a very similar technique for the gRPC layer. So if you see like a gRPC was running over sockets, so now we have done the design, which is the RDMA based design. Okay? So this is like the orange line you can see. Again, the latency, these are the small, medium, large messages, we can improve quite a lot. This is the gRPC layer evaluation. So this is the evaluation with actually deep learning with Inception 3 dataset. And so this again paper was presented in the HPC conference in 2018. So we did a lot of studies with all those different combinations like MPI plus X, because people want to see whether the solution delivers the best performance or not. So our solution is basically red bars. And the higher is the better. So across all the different nodes, different batch sizes, we are able to show that if you use our stack, you will be able to get good benefits. So what we have done, we have made a public release of this. So if you go to our website, this is the same website I indicated, HIDL, High Performance DL, you should be able to download this stack, RDMA TensorFlow. So if you have any InfiniBand cluster or even a Rocky cluster, you should be able to directly run this. And you will see suddenly your performance boost takes place. So then I indicated like the people are also trying to explore the big data, deep learning through big data, like Hadoop, Spark kind of things. So then this is a project we have been doing for the last almost 8 to 9 years. So if you take any of these big data stacks like a Spark, Hadoop, HBase, all those stacks, very similar to the MPI over verbs design, we have done this design over the native InfiniBand and Rocky. Okay? So this is the other project from my group called HiBD, High Performance Big Data. We are trying to combine again HPC and Big Data. So this currently is being used by, these stacks are being used by again 315 organizations in 35 countries. These are registered organizations. We have more than 30,000 downloads here. So this has support for InfiniBand, Rocky. It can also run over Ethernet. It has support for x86 as well as OpenPower. It also has container support. So even our MPI stack is also available with container because we have been allowing that to happen in the cloud environment. So if you take a look at some of the performance numbers, just think of very simple numbers like this is a RDMA for Apache Hadoop 2.x version. These are some benchmarks like Random Writer and TeraGen. What I'm trying to show here, this is running over the InfiniBand system. The orange bars are the traditional Hadoop. If you download from the Apache Hadoop, if you go inside, it actually runs over sockets. And sockets typically over InfiniBand, there is a module called IP over IB, which is the TCP/IP emulation over InfiniBand. So that's what is the orange bar. And now if you use the RDMA design, which is our red, you see almost you get an improvement by factor of 3x, 4x. Exactly same hardware. You are not changing anything, but with a optimized software stack, you are able to exploit more performance. This is another, the Spark design, RDMA Spark with high bench, very similar kind of things. This is a page rank. We are running over here almost 1,500 cores, 718 cores, and you can see almost 37%, 30% benefits you see using the RDMA stack. So what we have done is, so now since you have this RDMA enabled, let's say Spark, and now there is a deep learning stack which is trying to use RDMA using Spark, you should be able to get the performance boost. Okay? if you use our version of the Spark instead of the regular Spark. And this is some results we presented at the Hot Interconnect 2017. So you can see, like, compared to this orange line, this is the RDMA line. So you are able to improve almost by a factor of 2.6x without sacrificing any performance. So this is how we are trying to bring the deep learning over also the big data. So irrespective of how you are approaching, you go through the GRPC route, you go through the MPI route, or you go through the big data route, we are trying to enable the community to have better and optimized stacks. So with this, let me conclude here. What I presented is like scalable distributed training is important. I gave a lot of different kinds of examples to see how you can optimize and where you can optimize, and a lot of these things are publicly available so that you can actually enhance the thing. I also want to highlight this. This is some recent developments many people in this part of the world might not be knowing. We have been in this community for the last 18 years, so we have been providing a lot of support from the university side, but a lot of people also want commercial support. So now we have a commercial offshoot which actually supports all these libraries in a very commercial manner. We can be a part of a bidding, optimization, contract, all those kind of things. In fact, this xScale solution is also has been very happy to sponsor this event also. And we are actually supporting Lawrence Livermore National Lab, which is one of the largest national lab in US for the last 2 years through this effort. And in fact, last week, we also announced some integrated products called xScale HPC, xScale AI. So it will have like a single click deployment kind of things. We introduced this in the Open Power Summit, which took place last week in San Diego. So any one of you are interested in these, please feel free to take a look at these so we can also talk offline. So with this, let me thank all my sponsors, but more importantly, these are all my heroes. Every talk, I just come to Australia and give this talk, but a lot of my staff members are working quite hard. And what I presented today is not just like a 1 year's work, it's a 20 years work. We have been evolving, so I'd like to really salute all of them in each of my talk. So that is not the only, like all the people who have been working hard, I also need a lot of new people, okay? So this is like in Australia, so I want to advertise if you're a student, postdoc, research scientist, and you would like to come and work in my group so that your name appears in that other list in future talks, please contact me. Okay, with this, let me close here, and I'll be happy to take questions if you have now. Otherwise, I'm here today, and tomorrow I'll be able to talk offline. Thank you.